All right, so happy Saturday. So I think we're going to finish chapter 4 today. We're actually a little bit ahead of schedule, but I think chapter 6 will kind of hold us up a little bit. So I'm trying to kind of reserve an extra day, or so, to extra lecture period to make sure we're still on schedule. Once we're done chapter 4, that'll be all exam 1 material. So, all right. So we left off with an acid-base titration problem. We'll finish that one, and then we'll do redox, okay, which can be rather explosive at times. So we had this problem, okay, for our acid-base titration. Can you have titration problems with other kinds of chemistry? Can you have that? The answer is yes, right? You can have precipitation titrations. You can have redox titrations. An analytical chemistry course I used to teach at Cal State Fullerton, we did a precipitation titration. We titrated the chloride ion in seawater with silver nitrate. As you might remember, silver precipitates out chloride ion, and so by the mass of silver chloride you produce, we were able to figure out what the mass percent of chloride ion, and as a result, sodium chloride was in seawater. So that's one example. Another example with redox titrations, we did another lab where we titrated the amount of vitamin C in orange juice. That's kind of fun. People brought oranges and lemons and whatnot to the lab, and we had knives, dare I say, and we allowed students to cut oranges in lab. I don't know if that was the safest, but it was certainly fun. It was a lot of fun. As long as everybody was mentally stable, it was all good. Okay. So anyway, but this is an acid-base titration. Acid-base titrations are probably the most common. They're also used in pharmaceutical industry. My wife would tell me many times that some of the colleagues she had would have to do a titration. So a lot of drugs have acidic or basic properties, and so they use titration to quantify how much drug content would be in a tablet, for example, or an injectable solution. So we're not just teaching this stuff just because it's in the book. It actually has real-world relevancy. So with this example, they were titrating barium hydroxide with nitric acid. So in your flask, if you remember from Chem 107, your titration, typical titration, inside the flask you have your titrant. Okay, and in this case they're saying, well, the barium hydroxide is in the flask. We don't know what the concentration is, so we're going to titrate it with a known concentration of nitric acid, which would be in your burette. Okay, and so they do that. This is the chemistry of the titration. This is a generic equation for titrations, but you have to remember that built into this is the mole ratio of 1 to 2. 2 nitric acids for every 1 barium hydroxide. So you have to remember, at the equivalence point or stoichiometric point, the moles of H plus has to be equal to the moles of hydronium. Or excuse me, moles of H plus is equal to the moles of hydroxide. And so to make that happen, to have complete titration to the end point, you have to have 2 nitric acids for every 1 barium hydroxide, which has 2 hydroxides in it. So does that make sense when I say H plus is equal to OH minus at the end point? Okay. Sometimes they'll just say, oh, moles of acid are equal to moles of base, but that's not exactly accurate, because if you just say, okay, moles of acid is equal to moles of base, okay, then that's not quite accurate because it's not taking into account the mole ratio. Okay, so I always say moles of H plus is equal to moles of OH minus at the end point. Okay, that's more accurate. So we figured out what the moles of our base was. For the numerator, came out to this. We divided by 0.0300 liters. 2 questions I have. Why are we dividing by 0.03 liters? Why are we not dividing by, say, 80 milliliters or 50? Why are we only dividing by 30? And that gets us back to, what is the goal of the titration? The goal is to find the molarity of the original solution in your flask. So the original solution was 30 milliliters in your flask, right? We wanted to know what the molarity of that was, not the molarity after we did the titration. Does that make sense? Hopefully. So the goal of a titration, even if I gave it to you on a test question, you know, maybe even multiple choice, it'd be a good multiple choice question. The goal of a titration is to determine the volume of solution after titration, before, you know, the word original volume might be useful. So just consider things like that. The other thing is with sig figs, why do we have 0, 0 here? So because it's 30.0 in the milliliters, right, that's 3 sig figs. So 0.0300 is 3 sig figs. So sig figs, of course, always important. And going back to your days of Chem 107, when converting from milliliters to liters, for example, you got to keep the same sig figs. Right? Okay, so does anyone have any questions on what we left off with yesterday? Okay. All right. Cool. Now, what about the second question here? What is the barium ion concentration after neutralization is complete? So the key word here is after. So what volume do you think we're going to use to figure out the molarity of barium? Are we going to use 30 milliliters? Are we going to use 50 milliliters? Or are we going to use 80 milliliters? After neutralization is complete, what does that mean? It means after the titration is over. So what volume? We're going to use the 80, right? So the verbiage does, you know, you got to pay attention to the verbiage. But so after titration is complete, we'll have a final volume of 80 milliliters. Okay, so what that ends up doing to the barium, we can say, well, we know how many moles of barium hydroxide we have. Right, we know how many moles we have of that. So we figured that out just by doing the stoichiometry of the titration. So we got molarity, or excuse me, we have moles of barium hydroxide. How many barium ions do we have for every 1 mole of barium hydroxide? 1 to 1, right? So we have 1 mole of Ba2 plus for every 1 mole of barium hydroxide. So that means we have 0.00375 moles of Ba2 plus by itself. Okay, and then how do we get the molarity? What volume do we divide by? Do we divide by volume? What are the units of molarity? Moles of solute per liter of solution. So here the barium ion is the solute, and the liters of solution is going to be after titration 80 milliliters, right? Or 0.0800 liters. So, putting it in your calculator, you should get 0.047 molar barium ion. Why is it just 2 sig figs here? Because this was only 2 sig figs. And why is that only 2 sig figs? Because it came all the way from the molarity of the nitric acid, which was only 0.15 molar. Right, so that carried all the way through. So, what were the 2 main mole ratios in chemistry? This goes back to the very beginning of chapter 4. We have 2 mole ratios in chemistry. What are they? The stoichiometric mole ratio and the element mole ratio within a compound. This has both of them. Right, here's your stoichiometry, stoichiometric mole ratio. here's your element within a compound mole ratio. So do you see why I started off the chapter with there are two main mole ratios in chemistry? It's because they pop up sometimes both in the same problem. So that's the big picture. I like big picture stuff. If you get the big picture, then the rest of it gets easy. All right. Titrations, what do you think? Not too bad. They're all usually worded in this way. You know, you've got a volume and a molarity of the titrant, and you've got just a volume of the titrate, you know, and usually they're written in that way. Friday next week, we'll try to practice some of those. I've got a few. Okay. So that's acid-base chemistry. Let's do some redox. All right. So unlike acid-base, so let's think big picture again. With precipitation chemistry, what are we swapping? Precipitation chemistry. Okay, we're forming solids out of solution. We are swapping just cations and anions in general, right? It's a double replacement or double displacement from your Chem 107. You're just swapping a cation and anion between the others, and you get yourself precipitation chemistry. The only time that double replacement is not precipitation is when a hydrogen ion is being thrown around, okay? And then it becomes acid-base, right? So we're swapping ions in those two kinds of chemistries, but for redox, what's being thrown around and swapped are electrons, okay? So that's a big picture concept that I just want you to get down. What are the inherent characteristics of the three main kinds of chemistries, right? So with precipitation, you're swapping just any old ion except hydrogen. With acid-base, you're swapping around hydrogen ions specifically, okay? And with redox, you're swapping electrons specifically. All right. Nice big picture concept. Okay, so acid-base, H+, precipitation, all other ions except for H+. The transfer of electrons can be observed through what we call oxidation numbers of the atoms within these compounds that are involved in the chemistry. What you look at is you look at the same atom on both sides of the arrow, and if there's a change in this oxidation number, you know there's a transfer of electrons. Now, the oxidation number of an element is the charge that a single atom, quote-unquote, appears to have within a compound if all shared electrons are assigned to the most electronegative atom. That sounds like a mouthful. The word electronegative, what does that mean to you? You've probably heard it from Chem 107, you should have. What is electronegativity? What is that? Polarity. It has to do with polarity. When we look at an imbalance in electronegativity in a compound, in a structure, that leads to polarity. So the higher the electronegativity of an element, what does that mean? It means it more strongly attracts electrons to it when it's bonds to other atoms. So this goes back to sort of electronegativity with Lewis structures, and I'll show you an example of this right now. So you look at HCl, it's a covalent compound. In this compound, hydrogen is said to have a +1 charge, and chloride is said to have a -1 charge. And so the oxidation numbers for HCl would be +1 for hydrogen, -1 for chlorine. Okay, and so if I did a Lewis structure for this, okay, just to illustrate what I mean by this definition of oxidation number, you know, single atom appears to have within a compound. If we look at HCl, going back to Lewis structures, which you've at least seen this basic structure, right? Okay, if we look at the most electronegative atom, okay, chlorine is a 3.0 on the electronegativity scale, and hydrogen is a 2.1 on the electronegativity scale. So if all of these shared electrons are assumed to belong to the most electronegative element, as given by the definition of oxidation number, okay, that means that all these shared electrons in this bond belong to the chlorine, okay? So Chlorine normally has 7 electrons, but here it's got 8 around it. And as a result of that, it is said to have a -1 charge on it. Okay, and that's where the oxidation number of chloride comes from in HCl. And then of course, since hydrogen has no electrons given to it, it now has a +1. So we're used to thinking about the periodic table and just in general, group 1, cations are always +1, and then the halogens are usually -1. That's what we're used to thinking, but this is just painting it in the context of an oxidation number now. All right, so that's where the definition of oxidation number comes from. The rules for oxidation numbers come from that definition. Okay, if I did, let me do something a little different here. Let's compare OCl2 versus OF2. Okay, let's compare the oxidation numbers to that. Well, if I did a Lewis structure for it, OF2 is the same thing. Okay, so same identical Lewis structures, just swapping halogens between, right? Okay, let's look at the electronegativities. Of course, you don't have an electronegativity chart, and I've done this so much, I have these numbers memorized, but I just sit there all day long memorizing numbers. Okay, so I look at oxygen versus chlorine, and now I look at oxygen versus fluorine. Fluorine is the most electronegative element. So if I look at these, you can see how things look a little different when you write the numbers out. So the most electronegative atom in OCl2 is the oxygen, and so it gets 8 electrons around it. So what do you think the oxidation number is for the oxygen here? It's going to be -2 because it's got 8 electrons around it when it normally only has 6. Okay, so this is -2, and the chlorine, as a result, will have +1s around that because chlorine normally has 7 electrons, but now it only has 6 assigned to it. Okay, look at fluorine, with the fluorine, now the fluorines are the more electronegative atoms. So now, the fluorines are going to get their shared electrons assigned to it. And so now you get -1s for the fluorine, and poor old oxygen gets left out to dry with 2 less electrons. And so the oxidation numbers for oxygen change depending on what it's bonded to, right? So you can see how the electronegativity, based on the definition for oxidation number, it changes. So the rules for oxidation number come from the definition of what an oxidation number is. Okay. In Chem 107, if your professor did go through oxidation, redox, and oxidation numbers, they probably just went through the rules and they may not have explained what's behind all that, right? I was like answering the question of why. You know, it's always, why is it? Why? Why do we have all this homework? No. So the rules follow for redox chemistry. Okay, so for free elements, which are defined as all the diatomic elements, hydrogen, chlorine, the halogens, oxygen gas, also pure metals, you know, sodium, beryllium, any pure metal, iron, any element written by itself, P4, white phosphorus or red phosphorus. Not included in the list here is also rhombic sulfur, S8. Okay, any element written in its pure form, okay, is always given an oxidation number of 0. So we have to go through the rules of oxidation numbers before we can apply it to an actual chemical reaction and look at how the numbers change. Okay. Monatomic ions, they always just get the oxidation number of the common ion charge. So hydrogen normally gets +1 just because that's the common ion of hydrogen. Oxide gets a -2 oxidation number just because oxygen is usually -2, and so forth. You know, calcium, all the group 2 elements get +2 normally. Chloride -1. So if you see a monatomic ion, okay, you just get the common charge. Polyatomic ions, now the sum of all the oxidation numbers together have to equal the charge of the polyatomic ion. So for example, if you look at nitrate, okay, since oxygen is usually -2, okay, and there's 3 of those -2s, that means I get -6 contributing from the oxygen. You see that? So if oxygen's always 2 minus, and there's 3 of those, that's -6. What number on nitrogen do I have to add to get overall -1 charge? And that means +5, right? So it's +5 plus a -6 from the 3 oxygens equals -1. Okay, and this is how I get these oxidation numbers here for nitrogen and oxygen. Okay, you see how that works? So you have to add all the oxidation numbers together from each individual atom. Okay, let me write that out a little differently. So typically when we write oxidation numbers, we write them above the element in the compound. So if I took for nitrate, okay, what I would do is I'd say, okay, nitrogen is +5 and oxygen is -2. That's how you usually do it. So when you're writing out a chemical reaction and you want to see where the electrons are going, you would look for a change in the oxidation number relative to the products, okay, or relative to the other side of the arrow. So just taking nitrogen, it's 5 plus 3 times -2. Okay, and that equals -1 overall, right? And that -1 overall is how you get that -1 charge on nitrate. Any questions on oxidation numbers? So this goes for any compound. Sometimes you have a neutral compound that has no charge on it. All the oxidation numbers will add up to 0 at that point. Same thing with ammonium ion here. All the hydrogen is +1. So what do you think the nitrogen is going to have for oxidation? And it says it right here, that -3. But the reason why it's -3 for this nitrogen here is because all the hydrogens are +1. There's 4 of them. Right, so 4 plus a -3 gives me still +1 overall. All right. For neutral molecules, I think I just said this, sum of all the oxidation numbers is always equal to 0. So for water, oxygen is usually 2 minus, and there's 2 +1s from the hydrogens. Add them together, you get 0 charge overall. What about neutral molecules with metals? Okay, this is just saying it in a different way. All group 1 cations always get +1, all group 2 cations always get +2, and we've been doing that for a while, right? But if you add up the ions, they combine into neutral salts. 2 -1s from fluorine, +2 from the calcium, that gives you neutral salt, and so forth. Okay. Special cases for hydrogen. There is one special case for hydrogen where sometimes you have a -1 oxidation number for hydrogen, and those are in the hydride salts. So what do you call this compound? LiH. Lithium hydride. What do you call this? Sodium hydride. Calcium hydride. Okay, so occasionally you might see a periodic table where they list hydrogen above fluorine. Okay, in addition to listing it in the group 1 column. I don't see them too often, but occasionally you might see that. And the reason for that is just because sometimes hydrogen behaves like a halogen and can form hydride salts. So just like you have lithium chloride, you can have lithium hydride and so forth. So for hydride salts, that's the only case where hydrogen is -1. Otherwise, usually hydrogen is always +1. Fluorine, because it's the most electronegative atom, will always get -1 no matter what it's combined with. Right? That's because fluorine is most electronegative. Oxygen atoms are always 2 minus. There are a few exceptions to this. Hydrogen peroxide being one of them. In general, peroxides, oxygen gets a different oxidation number. So what do you think the oxidation number would be for H2O2? Let's see if we do that. Okay, so hydrogen peroxide, if hydrogen is always +1, unless it's with a hydride, but this is not a hydride salt, this is just a covalent compound. If hydrogen is always +1, then there's 2 of them. Okay, what's the oxidation number on the oxygen? Yeah, -1, right? So now it's -1. So that's an example of how oxygen might not be -2, but usually it's -2. All right. So those are the rules. Okay. I will give you these rules for an exam. I'm not going to make you memorize these. Okay. But I do want you to know how to apply it. Okay. So let's practice these. Okay. Calcium hydride. What are the oxidation numbers in these compounds?